Okay, we are in the Chapter 5 PowerPoint on energy changes, and today we're going to specifically talk about enthalpy. Which is abbreviated with an H, and usually we're just talking about changes in enthalpy, so that's going to be a change in, or a delta H. And enthalpy is, it's kind of like heat, but it's a special type of energy as heat. And what it refers to is the energy gained as heat by a system at constant pressure. So the enthalpy is going to be energy gained as heat at constant pressure. And we use the enthalpy because it's, first of all, it's easy to measure, and second of all, it gives us a good idea, although it's not the whole story, it gives us a good idea as to how much energy is involved in various chemical reactions. So because it's easy to measure, and because it gives us a decent idea of what's going on, we use it all the time. And just to give you an idea of what this might look like, we can imagine, well, let's just say a beaker that's open to the atmosphere. And since the atmospheric pressure is what's on the system the whole time, the pressure on the system is going to be constant because it's open, it's not sealed. And we might fill this beaker with some water and maybe try to insulate it so there's not much heat exchange going on. We can put a little container inside of this, and inside our container we'll put our reactants, and we'll run the chemical reaction inside our container. And that chemical reaction might release energy, or it might take in energy, but nevertheless, we'll assume it's releasing energy. We can then measure the energy change that occurs in the water using Q equals mc delta T. Hey, there, that's the energy gained as heat from the chemical reaction. The beaker's open to the atmosphere, and so the energy changes are measured at constant pressure. And so in this case, the heat change would be the enthalpy change. And again, this is used a lot in the lab and in the class in chemistry. Okay. So there's a few things about the enthalpy that we're going to go over here. Let me just write an equation so we can get an idea. We'll just imagine ice, solid water, melting, and we're going to imagine this as our system. So in this particular case, we have a certain amount of water that's solid, it's ice, and it's going to be melting. And the enthalpy change in the system is going to be dependent upon some stuff. So the first thing we want to recognize is enthalpy changes depend upon how much stuff you have. The states of matter involved, and the actual reactants and products. So for example, if I'm going to melt 1 gram of ice, that'll be a different enthalpy change than if I melt 2 grams of ice. It'll actually be double if you melt 2 grams. That should make sense. Melting 2 grams of ice, that's going to require heat going in, so it's going to have a positive delta H, a positive enthalpy. So 1 gram of solid water is going to require half as much energy as melting 2 grams of solid water. So it's going to depend upon how much stuff you have. It'll also depend upon the states of matter involved. So if I would change this to boiling So instead of going from solid water to liquid water, instead we look at the change where liquid water goes to gaseous water. That's going to be a different enthalpy change because it's a completely different process going on. And then it depends on the actual stuff you have there. So let's say I'm going to look at the boiling of liquid nitrogen. So liquid nitrogen going to a gas, the enthalpy change involved there is going to be different than the enthalpy change involved in boiling of water. Another thing to keep in mind is that if I change the process, so it's the reverse, so instead of boiling, we have instead gas going to a liquid, which is condensation. If you change the direction of a particular process, so let's just say going in this direction, I don't know what it is, we'll just say it's like, actually I think I might remember, it's 5.5 kilojoules for every mole of nitrogen you have. I'm not sure that's right, but I think it is. So if it takes 5.5 kilojoules to evaporate a mole of nitrogen, and that's going to be positive because you have to put energy into the nitrogen to get it to boil. If we reverse it so that we take a mole of nitrogen gas and condense it into a liquid, then we're going to reverse the sign. So the condensation of gaseous nitrogen going to liquid nitrogen actually releases this amount of energy. All right, I'm just going to write a couple chemical reactions here on the board with their associated enthalpy changes. So we're going to have 2-methanol, which is an alcohol, and I'll need to include the state. It's going to be a liquid, plus 3O2 gas. That's going to go to 2 carbon dioxide and 4 waters. Let's see, gas phase. And there's an enthalpy change associated with this. Delta H is a negative 715 kilojoules for every mole. And there's, on this slide, it's actually slide 12 on the PowerPoint, there are also 3 other reactions that are listed with the corresponding enthalpy change for the particular reaction. And this is listed, these are all combustion reactions. So this is called the enthalpy of combustion. Of methanol. And the second one down would be the enthalpy of combustion of ethanol. Looks like the third one down would be the enthalpy of combustion of propanol. And then the last one on that page would be the enthalpy of combustion of octane, which is a major component in gasoline. Now we're going to sort of look at this, look at the whole thing here. The enthalpy, this tells me that this value here is telling me how much energy is either released or taken in as heat if this reaction is carried out at constant pressure. Exposed to the atmosphere is usually the way we think about it. Combustion, that tells me something else. You might recall that combustion implies that you have a carbon-containing compound, in this case the alcohol methanol, that is reacted with oxygen, usually from the atmosphere, to form carbon dioxide and water. And combustion reactions, they release, see that negative sign there? When that delta H is negative, that tells me that when this reaction takes place, energy gets released as heat. And that energy is often used to drive cars, heat your clothes, dry your clothes, cook your food, all sorts of stuff. So this part tells me it's the energy released as heat. This part tells me what type of reaction it is. And this is the specific compound that's being combusted, which in this case is methanol. This sign here is an indication that, once again, that the reaction, when it proceeds, releases energy. So that's released as a result of the chemical reaction. The other thing that I want to point out here is when you see reactions listed like this, you have to pay attention to what is stated for the enthalpy change. Now if you look, this says negative 715 kilojoules per mole of methanol combusted, because this is the enthalpy of combustion. So this corresponds to 1 mole of this being reacted. Sometimes in your book you're going to see things written, it would be written like this. You'll see the reaction written as, let's see, it'd be negative 1430. So you'll see the reaction listed, and then you'll see a negative 1430 kilojoules, and you won't see a per mole listed afterwards. If you see the reaction listed like this 1430 kilojoules would correspond to the combustion of 2 moles of methanol reacting with 3 moles of oxygen to produce 2 moles of carbon dioxide and 4 moles of water. So you have to pay attention to that. If you see this per mole thing at the end, of course I'd have to change this number. If you see this, this would correspond to the combustion of 1 mole of the substance. And if you're ever confused about that, you just ask. And I'll be happy to tell you which specifically the enthalpy listed is corresponding to. But pay attention to those numbers when you're working through problems. Okay, I'm going to write a couple of chemical reactions on the board, and then we're going to have some questions for you to think about based on what we're learning about enthalpy. So we're going to write reaction A. That's going to be gaseous water going to hydrogen gas and half a mole of oxygen gas. Okay, and then we're going to list with that, it says a positive 241.8 kilojoules. Okay, B, we have H2 gas plus half O2 gas goes to H2O gas. And then we have C, 2H2 gas plus 1 mole of O2 gas going to 2 moles of H2O gas. And then finally, we have H2O liquid going to H2 gas plus half O2 gas. And next to this I have delta H is positive 285.8 kilojoules. Hope I had that right. I just want to make sure I've got everything set. I do. Okay. The first question is, if we are given this reaction, H2O gas goes to H2 gas plus oxygen gas, and we know that that enthalpy change is going to be a positive 241.8 kilojoules, what's the enthalpy change for reaction B? Well, let's look at this. Here, this reaction is exactly the opposite of this one. Notice, in this one, H2O gas is my reactant. Over here, H2O gas is my product. Here, H2 gas, hydrogen gas, and half a mole of oxygen gas, those are my products. Those identical products in this reaction are the reactants in this particular reaction. So I see that this reaction is the opposite of this one. It's the perfect opposite. And because of that, all I have to do to find the enthalpy change for this particular reaction is just change the sign. Negative 241.8 kilojoules. And just to give you an idea about this, this is an indication that if I want to take water and split it, so to speak, into its gaseous elements, that's going to require the input of energy. On the other hand, if I take hydrogen gas, you all know this, you've seen this. If we take hydrogen gas and we react it with oxygen gas from the atmosphere, that makes a little explosion. that releases some energy, and sure enough, that's what we see here with the enthalpy. There's a negative 241.8 kilojoules that's associated when hydrogen gas explodes. And you've seen that before. Now let's look at this particular reaction here. What would be the enthalpy change associated with reaction C? Well, I can figure this out because if we look, this reaction is 2 times this one up here. So notice, this is twice this. So I just multiply this by 2 and I have 2 moles of hydrogen gas. A half times 2 is 1. So to go from here to here, once again, we multiply by 2. To go from here to here, we multiply by 2. So you can probably guess what we're going to do here. We're going to multiply by 2. Let's see, that's about 242. What's that? Positive 480, excuse me, negative 484. Roughly. Because I estimated, I went to the nearest kilojoule, not the nearest tenth of a kilojoule. So when I multiply, if I multiply the whole equation, which I've done here, I've got 2 of these, I've got 1 of these, where before I had a half, and I have 2 of these. If I multiply the equation by 2, and I multiply the enthalpy by 2. Finally, we'll look at this particular reaction here. Hey look, this looks like the same reaction as the top one, and yet the enthalpy change for this bottom reaction is 285.8 kilojoules. Why the difference? Can you see it? Well, in this case, we're starting with a gas. In this case, we're starting with a liquid. So while the products are identical, the reactants that we're starting with are not. And if you start with different reactants in a different state, it's going to be a different energy change. What's interesting about this is we can actually find, by using this equation here and this equation here, we should be able to find the energy it requires to boil or condense water. Watch the way this will work. First, let's just recognize that this enthalpy change is different than this one. Again, because here we're starting with a liquid, and here we're starting with a gas. So let me just write this below again. H2O liquid, those are different, goes to H2 gas plus half O2 gas. And in this case, the enthalpy change is positive 285.8 kilojoules. We're going to use some of these tricks now to see if I can't figure out what is the enthalpy change, we'll say, for H2O liquid going to H2O gas. In other words, what's the enthalpy, oh, I wrote a liquid there. In other words, what's the enthalpy change for the boiling of 1 mole of water? Watch how this can be done. What I'm going to do is I'm going to take this first reaction here and I'm going to reverse it. So let's just do that. If I reverse this reaction, if I reverse reaction A, that means I need to take these products and put them on the reactant side, and take this product, and take this reactant and put it on the product side. So it's going to look like this: H2 gas plus half O2 gas goes to H2O gas. And if I do this, the enthalpy change, you've already done this, this needs to change the sign. So let's see, delta H for this is going to be a negative 241.8 kilojoules. Now what we're going to do is I'm going to take this reaction here and we're going to add to it this reaction here. So we can do that. Let's see, it's going to be a lot of stuff. I'm going to have H2O liquid from this. Let's see, this has got to be a reactant, H2 gas, half O2 gas. That's going to go to H2 gas, half O2 gas, H2O gas. And if I added these two reactions together, it probably makes sense to you that to get the reaction, or the enthalpy for this total reaction, I should just add these together. So I'm going to add positive 285.8 and a negative 241.8. And if you do that, you get a positive 44 kilojoules of energy. But you might remember, I've told you before, that if you have a reaction where you have identical reactants and products in the same phase, you get to cancel them. So here on the reactant side, I have H2 gas, and here on the product side, I have H2 gas. So they cancel. It's like a quarter going in and a quarter coming out of the vending machine. There's no change. I'm going to do the same thing here for 1/2 O2. Cancel the 1/2 O2, cancel this 1/2 O2, and look what we have left over. H2O liquid goes to H2O gas. And we have just used all those equations I presented to you to figure out what the enthalpy change is for the boiling of 1 mole of water. I go from liquid water, 1 mole of liquid water, going to 1 mole of gaseous water. That should be associated with an enthalpy change of 44 kilojoules for every 1 mole of water that ends up evaporating.